Okay, so here we are talking about something called Table I. Okay, Table I for us AP students doesn't really exist. In New York State, we use it, of course, for the New York State region. So it's something you're going to see, something I want to talk about. And of course, it's a table that lists chemical reactions with delta H's. Now, stepping back, I know you've been through this. I know you don't want to hear me talk about this again. But one of our reactions in our lab, we had hydrochloric acid, sodium hydroxide, strong acid, strong base, makes a salt and water. This is not the net ion. However, looking at the heats of formations of them, we know that the collective heats of formation of HCl, okay, I have that right now, and then of course of OH minus as an ion, and then of course sodium ion. So 240.3 was here. When you put them together, so you take sodium plus here, take hydrochloric acid here, and take the value of the heats of formation of OH, the collective heats of formation give me this total negative number here down to this point. And of course the products, their heats of formations, of course, that's aqueous, so therefore it's an ion. They collectively, the Na plus, Cl negative, and the water, very stable, collectively have lower amount of energy. Or I could say they result in a lower energy because more energy released. So when you add these numbers together, there's a greater amount of energy released. So this position represents the what? The sum of all the heats of formations of the products. And this position is the sum of all the heats of formation of the reactants. And when you subtract them, and of course you do products minus reactants, and we do so because we want to show that a negative number dropping. And as I said in class, the best way to think about this, I think, the reason why they do the products sum of the heats of formation, which by the way is the Goat and Hess's law, because its positioning of the state functions of delta H is based upon that, okay, really helps us here. But the reason why we do products minus reactants, the best way to think about it is how much energy is left. So if you release, if this is the free atom zone, this is the place of high energy, and you lose all of that to get here, okay, and you lost more than the reactants did to get here, to go forward, energy has to be given off. And we want this sign to be negative. So therefore, we essentially do products minus reactants. But the best way to think why we do that is because if you lose more energy, there's what? There's less energy remaining. So we say the potential energy of these products is lower than the potential energy of these reactants, or the reactants have more potential energy. And it makes sense. If it's exothermic, energy is being released, your reactants have a lot more energy in their bonds, if you want to think of it that way, than the energy in the bonds, of course, in the products. And so if you do the total amount of potential energy, we draw a line right here. Let's make this sentence be that line, okay? So we do a small number minus a big number, and that gives me the negative. So in Regents land, for our course, and we're teaching both, delta H is also considered to be the potential energy of the products minus reactants. Now, if you notice, these are solutions, and although this is a strong acid, strong base scenario, which really results essentially in H plus proton plus a hydroxide gives us water, and as I always say in my course, you only get that net ion reaction when a strong acid, strong base. That is heat of neutralization, okay? And that's always going to be exothermic. Add an acid to a base, it's going to feel warm because it's a spontaneous process to make the H2 a liquid. We'll talk more about that. But I want to talk about solutions today because it's the solutions essentially we call heat of dissolution. And so delta H has a lot of names as we're seeing here. Enthalpy that we talked about, it's not entropy. No, it's enthalpy. We learned that essentially that is what? The delta E minus the work done at the constant pressure and calorimetry that we solve for. But, okay, it's important to realize that the addition of ions in water and how they dissolve to give off heat, we have to understand that in terms of intermolecular forces again and bring that back. So before we do so, I want to talk a little bit about Table I. So Table I, the first third of Table I, has combustion reactions. And how do I know combustion? Well, I know a carbon-based fuel, look at these hydrocarbons, and oxygen gives me CO2 and water. And so that's classic combustion. Oxygen plus a fuel gives me CO2 and water. The CO2 is the most oxidized form of carbon, and the water. And these are very stable compounds. Notice the sign of delta G is negative. That means it's exothermic. Now, what I don't like about this table is they give me kilojoules. And they do a little star here. And that star, when you look at it, okay, I don't know if you can see from where I'm standing, but if you look at your table I, the star means that the delta H values are based on molar quantities represented in the equations. Molar quantities of what? That's too vague. We know that delta H is the Q divided by how much. Most of the time in our course AP it's mole, but mole of either something you're producing or mole of something you're what? Reacting with. So the top third reactions here, okay, are combustion reactions. And these reactions, if I can just move this down, these reactions, we would call these delta H of combustion. We would write delta H of the comb or the combustion. Again, many names, it's still enthalpy. And they're what? Negative. And that's because why? Because the reactants have higher potential energy than the reactants, than the product, sorry. So the reactants, which is, of course, an unstable compound, unstable because it has what? Higher potential energy in its bond still, okay? And when it becomes a product, of course, the delta H goes down. Now, let's go over some of these things. This is methane. It's part of your natural gas. Gives off energy. Here is C3H8. That's propane. That's in your barbecues. And this is octane. That's gasoline. Here is methanol. Here is ethanol. Okay, and of course, here is the reaction, very important right here, where we take glucose plus 6 O2s plus 6 CO2s and 6 waters, and that's cellular respiration. Notice the energy that that gives off. Hey, that is where we get our free energy from, okay, to drive all of our non-spontaneous living reactions, if you remember that. And of course, the reverse, you better understand, the reverse of the delta H is positive 284, and that's photosynthesis. And that's non-spontaneous, but more importantly, that's endothermic going this way. So, little tidbit about some of these things that surround yourself. Ethanol, if you didn't already know, is mixed in our gasoline in New York State. 10% of our gasoline is ethanol. Interesting to note, people put ethanol in our gasoline because the idea is that we're using a renewable energy source. And the idea is that we're taking corn that we're growing on a farm, and that corn, of course, produces sugar, and then we put in yeast, and we ferment, and kind of like moonshiners, if you watch the show, okay, we make essentially a fuel from that. And that fuel, of course, with oxygen, makes CO2 and water, so it does give off some emissions, but the idea is that we're not using fossil fuels, okay? We're using renewable things, the things that we're planting. And so we're mixing some, what we call some plant-based fuel into it. Now, some people also think that, well, wait a minute, we're producing, look, 2 CO2s here. And with burning, of course, of the octane of gasoline, there's 16. Now, there's a 1 here, and there's a 2. So it's an 8-to-2 ratio. So we burn 4 times as much CO2s and octanes, okay? So we're lowering the CO2 emissions. But if, notice very simply, what if we compare the heat? Well, look at that. All right, it's basically a 10-to-1 ratio. Okay, now this is a point I want to make before we compare. When you do the delta H's in table I, normally we do delta H's, delta H per mole, but that's not what they do in this table, which is a terrible, bad table. Okay, because look here, in octane gasoline, there's a 2 here. So that's the energy released, 10,943 kilojoules per 2 moles of gasoline burned or combusted. And when we compare it to the ethanol, that's the value 1367 released per 1 mole. You'll say, why do they do that? I don't know. In all other textbooks or words, we would divide this by 2. Remember, delta H is stoichiometrically related. So heat of combustion is always usually looked at per mole of this substance, yet they don't do it here for this reference table. But as I taught you today or the next day, understand what this is. So if this is methane, and I've got negative 890.4, and I want to know how much energy it takes, well, because there's nothing in front that applies 1, if I wanted to know how much energy it takes is released in 2 moles of methane being combusted, I would times that by 2. And if it was 0.5 moles, you would do that. So understand that delta H's, my friends, are nothing more, okay, than converting factors as well. Okay, you can't lose sight that it's also a converting factor. I say that because, hey, if I have 0.70 mole of methane, and I want to know how much energy that is, I'm going to take this negative 890.4, and I know that for every 1 mole, there's what? 890.4 kilojoules. And I can solve for that. And I can use delta H as a converting factor. And that's something they also do on the simpler test, the regions as well. Okay, so get that. But when you compare things, be careful. So back to my ethanol comparison, the idea that, well, okay, we put ethanol in 10% instead of the gasoline. Well, my friends, okay, we produce less CO2 emissions, CO2 being a greenhouse gas. Okay, if you compare it to the 1 mole of this reaction, that's a 2 to an 8. So essentially, there's 1/4 difference, right? There's 2 CO2s for the ethanol compared to the what? If you divide that by 2, stoichiometrically, that's a 1. That's going to be an 8. There's 8 moles of CO2 released. So clearly, that's a 1 to 4. And certainly, it makes a lot of sense why you would add ethanol to lower the emissions. Or is it that smart? Okay? People say, hey, plants are creating the fuel, we're not using fossil fuels, and we're lowering emissions. It seems like a win-win. However, let me think about this for a second. When you grow ethanol, what do you use? You use a tractor. People drive to your farm to work. You're burning gasoline. The process of getting the ethanol out happens inside some warehouse where you need electricity. Most electricity is using fossil fuels to create that. Then when you make it, you ship it on what? Trucks, okay? Again, all of that, and they've done calculations, and all of that energy, fossil fuel energy to deliver the ethanol to mix in the gasoline actually costs more. You're actually burning more fossil fuels to create the ethanol and bring it to the refinery to mix than you actually save. So we're producing or using up more fossil fuels to produce that. So there's, that's a negative. The other part is that instead of growing food, okay, on those farms, we're taking some of that area and we're growing corn for fuel, which means there's less farms for that. And I'm not saying it's a bad or negative thing, but there's some things you need to think about. And something else to think about, hey, look at the energy difference. 2 moles of the octane to 1 moles of methane. Remember, we got to divide this by 2. That's a terrible table to get per 1 mole. And this is about 11,000, right? So if you think about this value divided by 2, right? So it's 5, let's say it's 5,500. Okay, I'm just going to round it off and make this, and I'm just making a total amount of energy. We'll talk about it to comparative speakingly. So this is 1,400, okay, kilojoules. So you can look at that as, something close to 5 to 1, meaning something close to 4 probably, but let's just round it off to 5 to 1, meaning we get 5 times the amount of energy from gasoline. So what's that mean? If you mix some ethanol instead of the gasoline, the fuel you're using gives you less energy, which means you're going to have a lower miles per gallon. Therefore, you're going to need to fill up more and burn more fossil fuel. It gives off less energy. So it's for the same volume of ethanol you're mixing, you don't get the same energy as you would if that gasoline was 10%. So, so for all those reasons, you need to think about, is this really worth it? But it sounds good. All right. Any case, moving forward, we have another part of this table. Okay, and this is supposed to be like a heat of formation table. If you notice, we have elemental forms and we're producing compounds. So this is like a nice heat of formation table for them writing for you. Remember, heats of formation, a real table, okay, they just write the what? The number, they give you the product, and then they give you the value per mole. Except in this table, another bad table, if you notice the coefficient of 2 is in front. So this is the energy 3351 per 2 moles of aluminum oxide being made. So to get it per mole, you have to divide by 2 to compare. So it's really crazy little table, all right? And something we have to take care of when you look at this table. And again, these tables, normally in the rest of the world, except for New York State, we usually do them per mole, especially in heats of formation. These are always 1. And I can show you some things that are really like, a pitfall here. If I was to say which compound is more stable. Now I say stable, meaning what? Meaning when it's made from its elements, okay, we can probably say that if the delta H is more negative, or goes down more, we can say that the products have less potential energy, which means they're more stable and have stronger bonds. So if I look at my table here, let's look at the formation of ammonia and the formation of C2H6, which of course is your ethane. And so ammonia, it's 91.8, so that's pretty good. Oh, but ethane is negative 84, so you'd expect ammonia to be more stable, but don't forget there's a 2 in front. So you can divide that by 2. All right, so that's negative 40 something per mole. Therefore, just because there's no coefficient in front of the ethane, that negative 84 is a larger negative number and therefore more stable and has stronger bonds. Careful. I mean, there's some pitfalls with this. All right. Any case, but what I'm after today, as we go through table I, and is that I'm after the ionization reactions on the bottom here. So if we go down here, I'm after the ionization energies. So the last third, so the first third are combustion reactions. The middle part of table I are like bad heats of formation tables, where they're not doing it per 1 mole. And the last part is ionization. I'm being OCD here to straighten this out. Okay. Now, before I get started, so this part was the heat of formation sort of table with not per 1 mole. And then here we have our ionization. Okay. All right. Here's where we get our heats of dissolution. All right. Delta H of dissolution. Okay. Which means what? Which means that when we take a solid, and these are all ionic compounds, and dissolve them in water, we get the free ions. For instance, potassium nitrate, KNO3. When it dissolves in water, well, what happens is the K plus, we have the negative part of the water surrounding this ion. As we talked about already, this KNO3 is an ionic compound in a crystal, but water surrounds the positive on the end so that it no longer can attract to the NO3 ion in the other part of the crystal because, well, the H part, the positive part of the water, okay, is going to surround this ion. And so these guys have a tough time feeling each other and they're pulled away. And these attractive forces are called molecule ion. I call them the famous boyfriend, famous girlfriend. 2 famous couples come in. All the girls surround the good-looking guy and all the guys surround the good-looking girl, and they get pulled away. Same idea, okay? So KNO3, of course, is a crystal, and this crystal gets broken. But this attraction between the molecule, okay, that's really not going to work, okay? The attraction between this molecule here of water and this ion is called dipole ion attraction. You can also call it molecule ion, okay? Now, if you have water dissolving sugar, sugar's not an ion, you'd call that dipole attraction, okay? Any case, that's something to think about, but those are attractive forces, and of course this is the solvent. But what's the point here? The point here is that the delta H of dissolution of potassium nitrate is positive 34.89 kilojoules per mole. What does that mean? Well, that means that essentially that we are going to take energy in from the surroundings and it's going to get colder. So the delta H of dissolution, now what does that mean? Well, it means that when you think about where you're starting from potassium in a crystal with a nitrate ion. This nitrate ion is with potassium with an NO3, and this is a 1-to-1 crystal, okay? And it continues on. These are ions, stick together by ionic bonds. And then we have water, and what do we have? Well, you have H bonding in water. It's a molecular compound, so the positive part of the H, the electron deficient H, okay, is going to attract the negative end of the O, and that's how it's going to look, okay? And these dots here are attractive forces, H bonds, all right? And so it sticks together. So what does this mean when we have a delta H of dissolution positive 34? Well, it means, well, we have a potential energy diagram. This starts here, and it goes up because it's positive. And so this would be the free ions. They're not free, they actually have the what? They actually have the dipole ion here, okay? So this is the K plus. And sorry for that little. thing, and this, of course, is the NO3 minus. All right? And the difference there is that we're going to go up. Well, the question is why? Well, the question is easy. Why is it positive? Well, we got to consider the attractions or bonds before they mix. Before they mix in this state, in this potential energy diagram, the potassium nitrate and the water, even though I don't have water here, are collectively more stable with themselves than they are in this state when they dissolve each other. This is not as stable. And you say, well, why, Mr. Grodsky? Well, part of it could be that NO3 is negative 1. You're stretching a negative 1 over what? 4 atoms. So the coulombic attractions are really weak here. So water doesn't have a good, attraction for it. So it's not as stable. And clearly ionic compounds are pretty stable. Now this is a +1 to a -1, and water can pull them apart. It is soluble by our solubility rules because all group 1 ions are soluble and so are nitrates. But this arrangement just isn't as stable. And so to get to a more unstable state, party people, we have to go higher. And that's where you get your energy diagram to look like that. Now, of course, what I just drew was the pathway and maybe some activation energy. But it doesn't matter. The difference of where you start and where you finish, okay, is going to be that positive 34. And what does that mean? 34.89. And that means that somehow energy was absorbed in this process to help this along. Absorbed from what? Okay, well, absorbed from the solution to make this happen, so the solution's temperature drops. You drop KNO3 in water, the water temperature drops a lot. It gets cold. In fact, if you were to put KNO3 in a little baggie of, enclosed in a bag, and in that enclosed bag you have another enclosed water bag, and then you could pop that inner water bag and shake the salt inside another bag, that, my friends, would be a what? A cold pack, right? Ever had the cold packs where you pop the water and shake? What are you doing? You're shaking an endothermic salt whose heat of dissolution is positive. And why is it positive? Hey, because the attractions or the ionic bonds of individual compounds are more stable than the new scenario. It's not always the case because we have some of these salts are what? Negative, which means you can have a hot pack, okay? Not a cold pack, a hot pack for the same reasonings. You just use a different salt. And what that means, if you're going to be negative, like the case of sodium hydroxide, that means that the attractive forces between the ion and the dipole are more stable than they are as either the salt or the water attracting themselves. Something you must understand. So let's do a demonstration here. Okay. Possible. Okay. So I'm going to hit collect. Okay. At some point. All right. So I'm hitting collect. And we should see taking some readings per second. So I'm going to drop some sodium chloride. Okay. Now, if you look carefully, sodium chloride has a positive 3.88. So the heat of dissolution is positive. So that means that collectively, the new attractive forces between the solvent and solute particles are what? A little bit unstable. So it's going to take some energy. So if I pour some sodium chloride, table salt, okay, you would expect a temperature to do what? To drop. And we're getting a little bit. And let's add some more. And certainly isn't that impressive, but we do have a decrease in temperature. Okay? And I'll keep decreasing until I reach the saturation point. Okay? But essentially the temperature is lowered. Okay? And again, why? Because what? The products, the ions in this case, are more what? Or the ions with the water in these areas here are a little bit less stable. And we need some energy to get to that higher energy position. Now, not listed there is calcium chloride. Calcium chloride is called ice melt. Okay? So I'm going to pour some calcium chloride in this, and it would have a very negative heat of dissolution, much like sodium hydroxide. So let's drop that and see if we can see if there's an increase in temperature. Okay? So they call this ice melt because, well, we know that putting salt on ice melts ice because of the colligative properties. But just the dissolving of calcium and chloride ions does what? Releases heat, because the calcium and chloride ions collectively are more stable in this dipole to ion attraction. So we definitely have a new increase. And again, ice melt is going to give off heat when it dissolves, and that heat when it dissolves, of course, is very helpful in melting more ice. So we've got an increase there. And again, cold packs and hot packs are made that way. Calcium chloride, our last little piece here, is we have, again, heats of formation, okay? The heat of formation of calcium chloride, a lot of energy was released, calcium's +2, and then we have 2 negative ones in a crystal lattice. And of course, the heats of formation of the calcium ions, collectively the 2 chloride ions, remember it's a molar quantity, so you have to add everything, we are what? More stable, okay, than the original compound. So the difference where you start and finish, state function, is negative. And that negative, of course, is enough to really raise the temperature of the ice in the water, enough to actually melt ice just by the heat alone, okay? And that, of course, would make a nice hot pack, all right? And so it's important you can see that although this is still delta H, we're talking about dissolving, and you also now got to consider the new type of intermolecular forces. What? Dipole ion attractions, and whether or not they're stable enough as compared to their original compound. So in the case, for the last time, of calcium chloride, the reason why it's exothermic, okay, yes, heats of formation explain that for everything we've talked about this week, but another way to talk about this in terms of a solution and the intermolecular forces between the solvent, which is the compound doing the dissolving, breaking up the what? The salt, okay, and of course, we're not dealing with potassium anymore, so let's get that out of there, is to understand that this would be calcium +2, and this would be chloride ions, okay? Now the calcium +2, my friends, is going to be smaller than the K for a couple of reasons. Well, the best reason would be, I would say, losing 2 electrons. This is a really smaller ion. So water can really what? Attract this ion even more. So those attractive forces between the water and the calcium +2 ions, okay, are very, very, very stable because of the high coulombic attractions of calcium and its small size. Coulomb's law is based upon the distance, right, and the charge on top. So those higher coulombic attractions between the negative end of the oxygen to the calcium are a heck of a lot more stronger than we had with potassium and nitrate. And so that's going to make a more stable scenario. And so we draw the potential energy diagram. As you can see here, we start high, but we go low. We drop because this stability between the water and the ions in the solution is more stable than the sum of the attractive forces in the water for itself and the ionic attractions in the crystal, all right? And that's what you need to explain in terms of dissolving salts. Hey, exothermic, heat's released, the solution goes up. Endothermic, positive delta H, the solution drops. All right, hope that helps. Can't even see.